All right, perfect. Then I assume everyone is here and we can start. Let's see if I can also get this one maybe a bit smaller. One moment. Okay, cool. Yeah, then thanks for joining this workshop on how to work with Aqora. There will actually be two parts. So the first part I will do, it's basically on how to interact with the Aqora platform, going through our tutorial. And yeah, I think you can see the screen, and this is basically the H2 ground state energy calculation. And then afterwards, Julian is also with us on the call. He is one of my teammates, showing you this Q3AS, which you can also access from our platform. At the moment, it's a standalone solution, which has some hosted algorithms, like quantum algorithms that you can um, parameterize and then execute, and also have some nice visualizations around. All right, then let me start with this one. I would assume all of you to follow along. And also, if you have any questions or face any problems, then just unmute yourself and let me know or let us know. Then we can solve it or drop the issues you face in the Discord and we can resolve them. Okay, so I was presenting Aqora before. So we are doing in this current state something that you can imagine as a Kaggle for quantum. I assume you as participants of this hackathon to know Kaggle, the machine learning platform, or data science platform based on these online competitions. And we thought it's a great way also to explore use cases for quantum computing. Here we have our tutorial, which is calculating the ground state energy of the H2 molecule. Calculating the energy of the H2 molecule is basically something that a quantum computer should be good for. That's like kind of the original proposal from Richard Feynman back then to do these kind of molecular simulations and understand something about these systems, and the H2 molecule being kind of the smallest or one of the smallest systems. Um, we have this competition online, so if you go to this link that I posted in the Discord, you can first join the competition, which will ask you to sign up. So let me just sign in here with my Quantum Hacker account. And yeah, so once I'm signed in, now I can really join, and I will see here the download. Basically, everything, as this is a tutorial, is also documented here in the docs section. So here will also be all the steps, assuming you have Visual Studio Code or know how to translate it to your favorite IDE. We actually have also a Visual Studio Code plugin that you might want to use. But yeah, it's basically this tutorial. Like what I will do here is just to show you how to check out the use case on the platform, how to then work on your submission and actually do the submission after some iterations on your code. Once we will make the submission, we can see us on the leaderboard. You already see this account has already reached the score of 100 to be high. So here's the maximum score is 100. So what we can do, what we need to do is first install our CLI, which is just a pip the package. So from your command line, you can run pip install Aqora CLI. And once you have done this, it's similar to how you would check out a Git repository on GitHub. You can just copy this command, go in your command line interface, and then run Aqora template H2 ground state energy. And now you can, well, I can at least in this case say whether I want to just participate in this competition as myself or as one of the teams I'm part in, but I just want to do it as myself. And then what we will do is we will download the use case information, which in this case includes the H2 molecule description as well as the test data, and will also and the initial submission template, which we will go through in a second, and we'll also set up a virtual environment, which you see right now, so that you don't need to install or take care of the packages yourself. I see my internet connection is not great, so this is why it might take a bit. Well, my computer is downloading this. So far, so good. So you can all sign in, join the competition, and run this Aqora template H2 ground state energy command in your terminal. No complaints. So I assume yes. All good. Yeah. So I'm sorry. This seems to be a bit slow on my machine right now. Might be faster for you. It should be. Okay. Okay. Is it already finished for someone? So finally. So we see the use case is downloaded, which basically means I now have this directory on my computer. I can go here, list the files. We can see there's the README, there's a submission file, and basically what I can do now, just as a first step to show you, what I can already do is run Aqora test. So this is what we can do while working on our submission, as there's this uh, live grading functionality and the first submission template. We can just do this, and then we should see. Hmm, Actually, I'm wondering this one. Yeah. So we see well, there's some printing from the code base, but in the end, we see with this initial submission, we would get a score of 55. If you want, you could already now run the Aqora upload, which would then make your first submission. As my connection is not that great, I will skip this one, but feel free to do that. But then we can go into Visual Studio Code or any other. I think I can even do this, right? And we'll just open from here. And then we have this directory, and in the submission folder, there's this start here IPython notebook. There's also a Percival notebook. Percival is one of the quantum computing SDKs. It's actually from Condela, but for now we will just use the start here, which has a Jupyter notebook that explains the VQE, variational quantum eigensolver algorithm, based on this penny lane example. So penny lane being an SDK from Xanadu, which is also a quantum hardware provider from, I think they're based in Toronto from Canada. Yeah, I think it is Toronto. Right. So here we will have this code base, and I won't go through all the details here right now, but I would encourage you to check it out because it gives a bit of understanding of this algorithm in a, I assume, somewhat accessible way. You can also read this um, tutorial by Penny Lane, which might have even more information. But basically, you could consider this a machine learning algorithm, and the quantum neural network or this quantum circuit. I mean, is basically your kind of neural network on which you do some kind of gradient descent. And that's why you also have these kind of learning parameters that might sound familiar or look familiar from classical machine learning, some iterations, convergence tolerance, and some kind of optimizer. And if we want to improve our score, so one simple thing we could do is, for instance, just say we run for more iterations. We don't have a visualization here right now, but usually this works, right? And if I just change it from 5 iterations, which is in this submission template, to 50, we already increase our score from 55 to now 71. Yeah? And then we could do again the Aqora upload. which I would skip as my internet connection seems not to be so great. But yeah, so this is how you could just make yourself a bit familiar with how our platform works based on this um, on this use case of simulating the ground state energy of the H2 molecule. Yeah, once you do this, you will see yourself ranking on the leaderboard. And then the use case that we bring for this hackathon is actually one that we had online as a virtual competition last year, which is on clinical trial optimization. So similar to the other one, you have this overview here. You can, oops, sorry, join the competition and see in the end what it means to optimize a clinical trial is basically meaning to optimize this quadratic binary optimization problem, for which usually quantum computers seem to be a good fit. And yeah, I won't go through all the details, but as you can see, so here you can browse this use case and understand what it is about, how the data sets, data types look like, and so on and so on. But from here, I would now first hand over to Julian. Or maybe first, no, before I do that, I should ask, are there any more questions for this H2 ground state energy calculation tutorial? For those of you who have tried to follow along, did it work? Yeah, I see Chiara nodding. Yeah, there's otherwise drop the messages in the Discord or here. And yeah, then now handing over to Julian, who will give a quick introduction of the Q3AS, Quantum Algorithm as a Service, where we have hosted some algorithms and also actually which you can use to work on this challenge without the need to understand all the details of quantum computing, but can make use of these hosted algorithms and find the right parameters to score high on the leaderboard. Thank you. Julian, the stage is yours.
Hello, hello. Can everyone hear me? Is the mic on? Cool. Can everyone see my screen too? Yeah.
This I
All my
can't right
private
now.
conversations.
No, I only see you. Oh, wait. Ah, yes, I think I can see your Wikipedia.
Okay, perfect. Um, Amazing. So, let me go to Q3S here. So, let me show you. So we've brought together some tooling around using some well-known quantum algorithms and developed this tool here called Quantum Algorithms as a Service, Q3AS. You can go visit it at, let me post it in, can I post in Zoom? I don't know where the chat is. Maybe you can post the link to q3s.aqora.io. And yeah, so it's really easy to get started. You can log in with GitHub or Google, and you'll be presented with this dashboard. It'll be empty, of course, for you when you first log in. And I'm going to show you some of the things that you can do with it. So first things first, we have to go create an API key. You click here, you give it a name, it'll give you an API key. And then you can copy those credentials into your local repository. I've already set up a local repository. Let me go there and open it up in VS Code. Yeah, so like I said, you can just pop in your credentials, and then you can start playing around with it. So here, let me make this bigger. I've set up a little demo about how to use Q3AS, in this case to solve a couple of different types of problems. Um, So the first thing we do is we load our credentials for our Q3AS client. Um, Here we just do pip install Q3AS to get the client. Um, and in this example, I'm going to be working with MaxCut, which is an NP hard problem. Let me see if I can. Yeah, let's do MaxCut in Wikipedia. If you all are not familiar with the problem, it's essentially how to create a bipartite graph out of a graph where you have the maximum number of edges between the two subgraphs. And so it's an NP-hard problem. It's often used in optimization things to figure out, where there are strong dependency links between certain subgroups and things. But here it's a nice problem to visualize. So we set up our graph, um, and here you can see this is the graph straight from Wikipedia, but it's just 5 nodes and 6 edges. Um, and what we do is we load that into uh, what we call one of these Q3S applications, which uh, translates our domain problem into a quantum problem, um, or rather, quantum-friendly information. So from that graph, we can abstract a Hamiltonian and use that Hamiltonian to do VQE. So Yanis just showed you how you can use VQE to solve something like H2 ground state, which is basically you have a molecule, you want to know what the lowest levels of energy are for that molecule. In this case, we're doing that same kind of optimization problem, but instead of looking at molecular structures, we're looking at these graph structures. And yeah, iterating on this optimization problem where we have this Hamiltonian and we feed it through a quantum circuit and get these estimation results and try to lower the estimated values. So here we build our VQE problem, feeding it in this case, the MaxCut application, and then we send it to Q3S. So Q3S will create a job with a demeaning sounding name. Um, and so here I can see it in my dashboard. Um, and here it's already completed. And we can see the way that this estimation has evolved over time. And we can see that we've reached some kind of equilibrium state here. And basically what it does is it tries to find yeah, the optimal solution. And of course, this is like a noisy kind of interface that we have here. So we're looking at the solution with the most samples. Both of these are actually valid solutions. They're just kind of the inverse of each other. But we can see we have 2 nodes and 3 nodes on this side with 5 edges connecting them. Here we have other information about the problem that we sent and both the ansatz that we built as well as the Hamiltonian that we used. Here in the console, I get the job back, and then I can use the results of that job to do whatever further stuff that I want to do with that. Um, yeah, and so we use Q3S to do stuff like MaxCut. There's other applications here um,
Ian,
because, yeah.
maybe quickly before you do this next one, there was one question by David, where
Uh,
in the chat, where is the documentation showing how to convert a domain problem into a quantum solution? For example, max flow, and what benchmarks do you have?
Sure. That's a great question. So right now, so this is fairly new. We put it together fairly recently. Was it Aqora? I can pull it up. Yes. Okay, wait, let me just go and bye. So, um, da, da, da. You go to Q3AS. Oh, Q3AS. I don't know why that's not appearing. Yanis, do you know what's going on?
No, the site you just introduced looks fake. Is it your browser or is it,
I
no,
don't know.
what if you ignore it?
Ignored? Ignored.
Yeah.
All right. Um, that's a good question. Anyways, so yeah. So here you can find the documentation. Here the same example I've just given here. In the reference doc, we have some of the applications that we've been putting together. We're like I said, it's brand new, so we're putting together more applications all the time. Here's the max cut one. I was just about to show you the Cuba one. Um, but essentially, the applications are super simple. They're just about taking in some kind of domain space and outputting a Hamiltonian. I think benchmarks are slightly difficult. We use standard algorithms for Qiskit. It really depends on the hardware that you run on. So we use a simulator from Scaleway to do our estimations. Obviously, you could also run on real hardware if you wanted. Um, but yeah, it really depends on also the ansatzes that you decide to use for your Hamiltonians. I mean, the whole point of Q3AS here is to take in a domain space problem, convert it into a Hamiltonian so that you can use it with an ansatz and then visualize your VQE flow. But under the hood, we use a pretty, I would say, kind of state of the art, you know, SciPy, minimize, and yeah, the classical algorithms that you're familiar with. So it really depends on the simulator and the hardware that you run it on for performance, I'd say.
Yeah, there was the other question, what we charge for this. So right now, as Julian was said, it's a new thing we put together. So you get free credits in the beginning. I think it's like, is it 100 or 100,000? Julian, I think you have a better overview what you can do with that. Um, so I think that's already, you can do quite a lot, right? For now, for free.
Yeah, you get 100,000 credits, which is kind of an abstract amount. But you can see right here, I've used 30 credits for that um,
Yeah,
um, that problem.
right.
So it depends on the problem size, the number of iterations, how fine you want to optimize down the runtime and that kind of stuff.
Yeah. Right, thanks, Julian. And then the question, so you're simulating quantum on regular hardware. David, yes, this is also correct. So we are using a simulator at the moment. I don't know how many qubits it would have at maximum, Julian, how deep it can simulate.
I think it simulates, so it depends. There's different ways of depending on the complexity of your ansatz on your quantum circuit. There's different ways that you can actually run the simulation. So if you use a fairly simple circuit like this, I think you could actually run up to I, I think it's like 200 qubits. Um, But depending on the complexity of your circuit, it's usually capped off around like 60 something, I think. Um, something around there.
Yeah.
Um,
Yeah.
it
Uh,
really depends on the type of simulation that you use.
yeah.
Um, so, but
Right. No, it is right, David. As I see your next question, what's the advantage of just running the native algos? No, I think this is a very fair point that quantum in this current stage, like is the critics, right? So the as long as we don't have quantum advantage, you by definition don't have anything of an advantage of running on quantum hardware. So we have these noisy devices at the moment that like are about to surpass really what you can do classically. And I guess once we have this kind of hardware, which is expected to come, well, according to like timelines, roadmaps from companies like IBM and Quantinuum in 2 years, then there's really the use of doing that, right? So at the moment, it's more for experimenting. So any quantum algorithm at the moment, you can run on the hardware, but it's noisy and you like don't get anything out that you couldn't do classically. And I hope
yeah,
this statement is right. Like there might be some edge cases where it's a bit questionable, but so basically what you do at the moment is most of the time you simulate the quantum hardware, which is basically you could do it on like use classical algorithms, right?
I mean, yeah, you can also run, of course, on real quantum hardware. It's just gonna cost you a lot, to be honest. Which, yeah, uh, like Yana said, there's no real advantage to it at the moment because we're not there yet, unfortunately. But I mean, I think the quantum community at the moment is looking at one, how to, I mean, I think the big questions are what kind of domain space problems can you uh, find like a more quantum native problem to solve, and that basically the translation between real world to kind of this quantum domain is the interesting thing to be looking at for, when we do have the hardware to actually start running some of these larger problems. Are there any more questions? I don't know where the chat is here.
I see it on the right. No, David, you said and was saying thank you. So yeah, thank you for those questions, David. And I think it's important because there often is this misconceptions about quantum computing and like what's now the current state. But so just to from my perspective, at the moment, it's the industry is rather optimistic. You might have seen like well on the one side these announcements by Google, but also a few optimistic statements this year. Well, I mean, people like Bill Gates, or I think who else was it? Others saying within these next 5 years they would expect commercial value from quantum computing. It seems we are somewhat on the edge of getting to this 50-ish, 50 plus logical qubits with which you could do then things that you cannot do classically anymore. And there's a few things we know we can do then, like simulation of molecules, but there's likely others and it's not all figured out really what we can do to understand how we can make use of all this quantumness. Like there's a few algorithms we know, but yeah, so it's really experimental, and that's also why we provide this tool because the idea is just to play around and get an understanding and see where it can all go.
Yeah. Yeah.
Hey,
And like this tool right now is focused around VQE, and QAOA, but there are also other quantum annealers and stuff that are being used out in production as well. Edward, do you have a
hey,
question?
Junior, thank you for I'm joining this kind of late. Just figure out this link saying yeah. You want to after me real quick? Like this code three is like kind of simulation, or my framework is like a algorithm framework.
Yeah, basically, Q3AS is a tool for running at the moment VQE, variational quantum eigensolvers, in order to solve certain domain space problems. So the goal here is to provide visualization to see how well you've matched your problem with certain ansatzes, certain simulation techniques on different hardware and those kinds of things, as well as just providing simple tooling around translating domain space problems into quantum.
Got it. When it comes to the hardware, so what kind of hardware will make it compatible, or like D-Wave system or some other?
Right now it's all Qiskit based. So we run on simulators and Scaleway. But yeah, it's all digital circuits.
Oh, got it. But still on simulation side, right? Not on real hardware. Mm.
Yeah, not in real hardware. Yeah, I mean, so the we could potentially offer Unreal hardware in the future. But it's one of those things it's very expensive to run on real hardware at the moment. Um, and yeah.
So regarding this algorithm, you guys handwrite anything, or you guys use some like library like open source ones called Libra OQS?
I'm sorry, I didn't understand the question.
Yeah, so inside your system, you use some like open source library, such as
Yeah,
Libra OQS for
so
all
this
those like
is
circuit. Uh,
this is all open source if you want to look at it. And see why. So it's all in here. And you can look at the libraries that we use. Oh, not there. Da, 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 da. Where did I put it? Maybe it's there. Oh yeah. Um, yeah, so I mean we basically just depend on Qiskit and oh the backend that's true. Oh the backend is an open source. Um
yeah,
yeah, so I mean for the actual optimizers we use yeah, just kind of standard open source tools for the actual optimizers. Um
got it. Mm.
yeah.
So I just dropped the link, which is hosted on the GitHub called Libra OQS. So have you heard about that one?
Oh
Have you
cute.
heard about that one? Yeah. If you check that, it's a CPP based system. We use that in our Gopher security. Uh, Kind of have all this Crystal Kyber QEM implementation, right? So we use that heavily. We also customize something into the Gopher security system. I think that's good library. They can take a look at it, but I don't know how you can align that label OKS with your system to be make it more compatible the algorithm, especially QES, right? There are a couple of so come to the quantum protocol, there are a family of protocols. The Kyber is a one. You do the quantum encapsulation mechanism called QEM, right? Like in a way you figure out on both parties and you figure out the handshake protocol, right? Which is they end up getting quantum key. I use that quantum key to encrypt traffic and then other side decrypt traffic, right? So it comes with a kind of encryption, decryption, which already make the quantum resistant, right? That's part of that's benefit of the QEM
Right.
out
I
of
mean,
this QS.
so I think there's I mean there's lots of applications for quantum.
Mm-hmm.
I mean quantum cryptography is definitely one where everyone's kind of counting down the days until we get to Q day. And there's lots of people working on the quantum internet and those kinds of things. As well as with that, there's quantum sensors. There's all kinds of applications for quantum. I think specifically what Q3AS and also what Aqora looks at mostly is looking at basically quantum algorithms for solving problems. Um, so we would less be looking at, let's say, um, a quantum cryptography solution and more
Mhm.
looking at algorithms for prime factorization, for example, which obviously has, huge implications in quantum cybersecurity or in cybersecurity in general, but it's more about designing algorithms to solve problems faster and better. Whereas I think, yeah, quantum cybersecurity or cryptography, yeah, it's interesting, but it's almost like a whole nother domain, I
Got
think.
it, got it. Mm.
Yeah. Cool. Any other questions? All right.
Oh,
Maybe
wait.
I want to
So
go to.
um what interesting ideas like have you thought about this Hugging face for quantum computer? Like the
I,
Hugging face is for AI, right? So
yeah, I think Janos can talk
Yeah.
about that.
Yeah, no, actually, I was in my initial presentation, I was also saying that it's our goal. Yeah, it's our vision to be the Hugging Face for quantum. Yes.
got it, got it. Mm.
We have started with this Kaggle for quantum approach to make an easier transition from hackathons and provide this way for companies to explore the technology. But we want to make this transition now to be something like that. There's also, I mean, there's the algorithms, but there's many layers in between that we yet have to figure out and are evolving. Like there's the transpilation, the orchestration process, but also error mitigation and error correction. Um, so there's really a lot in this stack with different things that you could swap then. So we certainly see the value that such a platform will bring and are on our way to build it and provide it.
That's great. Yeah, this is about your system. I have a follow-up question is like hardware thing, right? So, what do you guys see? How many years ahead of that quantum computer hardware can be deployed? I mean, I'm not saying that low cost. I mean, even a certain amount of money is still very expensive, but still can commercially used everywhere. So, what do you guys see? Foresee?
Yeah, so the question is when we will have kind of a
Yeah,
commercial
yeah,
quantum
yeah.
advantage.
Yes,
Yeah,
yes.
that yeah, it's a good question. Probably I shouldn't give a prediction here. So what we see at the moment is like the industry is getting ever more optimistic that we will have quantum advantage soon. So quantum computers that can solve something that classical cannot anymore. That is of use. IBM just had an investor day earlier this week where they moved their prediction forward from 2027 to 2026, meaning next year they want to demonstrate it, which is amazing. But yeah, it doesn't mean that it's of economic value, right? It would probably still be just more expensive. Um, so far, the roadmaps have been like really been implemented the way they had been predicted, or at least extremely close to it. And by so meaning at the moment, so once we would have such hardware, would still be a bit, well, I mean, it would still be small, and then we will get to these fault tolerant computers by now these prediction also 2030, maybe even 2029-ish. Um, and maybe in between already, we will have this quantum economic advantage, maybe afterwards. But like from our perspective, like being in the field, we at least see it's getting ever more important to get quantum ready and understand and explore this technology, like from the industry side, to stay ahead of the curve, right? Because it will be a
Mm.
bit like a ChatGPT moment, likely that from one day to the other we have this hardware and then no one knows what to do with it or how to use it for them, and then suddenly it will be this rush. At least it looks like right now, but well, we will see.
Mm. So we're in a conversation with Gardner about the vendor briefing, right? So their conclusion is saying, hey, 2025, where quantum will be a big buzzword, and then come to massive adoption that would go until like 2029. So there will be like 4 years of in between the gap. It comes to massive adoption, right? I don't know. What about that side? Do you have any comment?
Um, no, not really. It could be,
Uh,
yeah. Maybe it's earlier. I mean, I think like our perspective on this, we take analogies from the AI field, which probably
mhm.
will work to some degree, but not fully. And we see that with this quantum supremacy that Google demonstrated, so doing something, but that's not useful. It's probably, or it might be like a GPT-1, and we would see quantum advantage maybe as a ChatGPT or maybe GPT-3, and then the economic quantum advantage of fault tolerant would be the ChatGPT moment. But yeah, we believe we would be somewhere in between, and then yeah. One certain problem, at least at the moment, it looks like a certain problem, is that we will not have enough people that know how to use the quantum computers,
Got it.
at least to
So
make
is
use
that true?
of all of it.
So there's a rumor saying Google shut down these quantum chips. Is that true?
Oh, I have no idea. I don't know.
Mm. Yeah, I checked the internet. I also heard about from some other places say they shut down quantum chips without any reason.
Okay, well, I heard for the first time. Could be.
Uh-huh. Got it. Uh, one interesting angle is, the quantum computers that can double-edged sword, right? So the other side, you get benefits, you get a super faster computer like the Google Willow chip, right? And solve problem in 5 minutes. Otherwise, take like 10 septennial years, right? Longer than life of the universe, right? That's for a benefit side, right? So on the other side, which is quantum threats, you guys probably already low, which is harvest allow, decrypt later, right? So all the modern PKI based infrastructure is based on private key, public key, right? The RSA, for example, and then everything is safe, even your crypto wallet. Yeah, you still believe that your Bitcoin is out there. Nobody can transfer all the if they don't have a private key, right? Which is not true when it comes to quantum computer. Where is the quantum threat, quantum resistance, which is cybersecurity perspective, right? So I think I kind of need you guys' opinion. Um, from that side, literally, and Gopher security, as we demonstrated, we have this day one. If we deploy Gopher, we have the day one protection and make it your data in transit, data at rest to be quantum resistant, right? So it's kind of still early stage. You evangelize this quantum resistance, right? For something which is quantum computer, not even ready, right? So what do you guys? What's your comment? Hey, come to the quantum protection, quantum threats, all the industry, different vertical, what are they preparing, or do they already think of this quantum threat already? So what do you think?
Yeah, I mean, oh, sorry, Join if you want to go first.
Oh no. I mean, yeah. Personally, I feel like, and this is just personally, like so quantum advantage, the moment that Yannis is talking about is about finding a specific problem that a quantum computer can do better than a classical computer can do, and then also to take that and to scale it up to an economic size is probably going to take a little bit, but then. I mean, to the point of, I mean, how many logical qubits does cracking an RSA key take of
And
Oh,
thirty-two.
significant size? It's like thousands, no? 2,000?
yeah, it's
Yeah.
many.
So
So Chad Chad
it's
is
gonna
researcher
it's
has
gonna take
cracked
a
the
while,
32.
but at the same time, there's vast amounts of data that is currently sitting there. And it's not just about the data movement, right? It's also about historical data. Um, and yeah, I mean, I would hope that NIST would come up with, standardized and regulated quantum, proved algorithms of
Actually,
resistance.
that's what I wanted to say. So it's not they added it last year, right? I think it was added.
I think they're currently in their last rounds of
Oh,
finalists, but they haven't.
oh,
I
okay.
don't think they've specifically picked.
Oh, I see. I
Yeah.
see. I thought it was already, but at least like Apple, I think announced last year they made their iMessage quantum resistant. Though I think so now I hope I don't see anything wrong here. But I think there's some time like with some of these quantum resistance algorithms, the question is whether they will really be quantum resistant. Yeah, I think there was one or two that got busted. But I hope I'm not saying something wrong here.
So my answer is that for example, the Kyber we just know inside out, right? So it's kind of the whole world, the scientists, the researchers come together, submit that a quantum resistant protocol based on that is a module, right, that is super hard to solve that problem, right? So that's why that's a whole community of NIST and selected Kyber. Yeah, they claim to be quantum resistant based on that is problem, right? But it really because the hardware is not there, it's hard to prove that it is quantum resistant, but it is what it is. So that's what we can use the most advanced protocol to make our product be quantum resistant. When it comes to security, security like stress side, it got to be like forward thinking. We got to be like deploy that pre-prepared, right? Otherwise, it's just too late. They can record your historic traffic, right? Like your TLS traffic, like your banking, those traffic, and then when quantum computer is ready, they can already figure out everything, right? Even a crypto wallet, your private key. So that's why that that security side, I mean, lot benefit side, security side. That's why the whole industry all have to be prepared before that's ready. So I'm wondering even like crypto currency, like Bitcoin, like Ethereum, like those are communities they haven't solved about. They don't even have a roadmap of, hey, how to make the blockchain to be quantum resistant, right? Bitcoin, Ethereum has some proposal, but not Bitcoin community. So I would say Ethereum could be one of the only, uh, only one of the many blockchain have the kind of an initial proposal to 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 think of that side, but not Bitcoin, not many other projects.
I don't know the specifics of the blockchain industry in this, but yeah, I mean, I guess you should. There's also quantum key distribution, so not using this. Like, I mean, I guess it will be a combination, but you can like agree on the public-private key to through
Is my level
well
about it? Or
through
can,
some. Oh, sorry, it might be me. But anyways, I was just wanted to throw this in. But no, sounds good.
mm, okay, okay. Wait, so quantum key distribution, do you guys say any design architecture or how does it work? I mean, it's essentially decentrally.
This is, I mean, this happens on the hardware layer. So you really, well, I think you generate these bell states, and then you can basically say whether someone like you, because you transfer these quantum states, you could tell if someone was attacking you from the middle. So that's another way of defending, I believe. But it's not like these fields, like the quantum and
We
security
lost you.
is not my
Mm.
expertise.
Yeah, I think Giannis's internet isn't too good. But
Yeah, yeah,
but
Yanis, you mute yourself. Oh,
yeah, I mean, essentially, uh, eventually you're um, basically entangling two um, quantum states and sending one, and or multiple Bell states, I think. And you can tell if someone's been listening in. Essentially, if someone taps into your basically your transmission, you will at least notice that someone's listening.
mm,
So you know that that key is no longer valid.
oh. Hey,
But
so how does that quantum key work? It's like the public key, private key pair. You know, in the classic encryption, where each party will have a key pair, right? Private key, public key. So in order to communicate each other, you need to exchange that public key. Like I send you a message, I need to use your public key. So to encrypt anything, I use my private key, right? You when you got message, you can it's like DH. That's where you need a third party or should or also similar control plane to distribute this public key, right? and let the both parties hold the public key mutually. So, I mean, I try to understand, is that the same case for the come to the quantum key? They
No,
also need a,
I don't think they're asymmetric. But
mhm.
I'm like I said, I'm not super well versed in quantum cryptography. But you can basically think of a quantum key distribution as an alternative to Diffie-Hellman. But I don't think they're asymmetric at the moment. I think it's all about symmetric cryptography. But I'm not 100% sure on that, to be honest. I don't really know how the Kyber algorithms work.
I got it. So,
But like I said, I mean, so Aqora is mostly working on a different side of the quantum universe. Like I said, there's lots of different um, quantum
so uh,
um, technologies currently being developed.
yeah, so with this opportunities, I actually talk about the quantum key distribution because we use Kyber, right? So we use Kyber. Um, the Kyber protocol can give you a chance. You already just send one round trip message. You already can figure the encryption key, which is symmetric one in the classic terminology, right? So I don't feel like anything you have to distribute this quantum public key and to both parties in order to communicate it, right? I don't see that that part which is needed, right? So, for example, in our Gopher case, we have figured out this. We have designed this two-phase handshake protocol. So, on the below side, which is classic end-to-end encryption, like the WhatsApp, right? So, on the phase two, on the phase one, if we, like I said, there's an initiator, the responder, initiator just send a message using a Kyber protocol to the other side. So the other side and they can respond back. So just one round trip, they can already figure out this quantum encryption key. So, uh, uh, yeah, there's no need. There's no need to. There's a control plane. There's third party behind responsible for this key distribution. I don't see any of that requirement. Mm.
Yeah, I mean, so like I said, there's lots of different technologies at play. I mean, people are trying to design the quantum internet right now. Right, to do quantum key distribution, you can't just use a normal, you can just distribute those bell states on the normal internet, right?
Mhm,
Um,
mhm,
so you need a whole new infrastructure for those kinds of things.
mm.
So, yeah, like I said, there's a lot of things being developed at the moment. Um, and I would say the quantum space at the currently is a very experimental place where it's about research and possibilities. Um, and there are definitely people that are working on some more practical use cases and real world use cases. But yeah, I mean, for us personally, it's just about introducing people into the quantum space, helping people get up and running with things that may seem scary at first, as well as a space for researchers and professionals to kind of show off their latest new thoughts and processes and algorithms for solving problems. But it's a very experimental kind of, which is a beautiful place to be because it's not as competitive as I mean, difficult to say, but it's an ecosystem that shares a lot, which is nice.
So it seems like that we've wrapped up, unless you have anything additional to go through. But thank you so much for your time. And yeah, we appreciate all the questions. Edward, you're very passionate about this, which we love. But yeah, feel free to let us know if you have anything else, and we can wrap this up.
Thank you. Thank you.
Thank you,
Oh,
Megan.
thank
No,
you,
it's from
everyone. So,
yeah.
mm.
Sorry, my connection seems still to be bad. I just want to say for the hackathon, then we encourage you to work on this clinical trial optimization use case. The link is in the Discord. We will be off like soon because it's getting night here in Europe, but I'll be back then tomorrow to check in if you're facing any problems. And yeah, then happy hacking, and thank you for being here for the workshop with us. And yeah, I think quantum is exciting to explore now these days. And yeah, have fun.
All right,
Definitely.
so
Thank you so
lastly,
much.
yeah, lastly, so maybe we can off some conversation to the offline and connect the LinkedIn. So like Julia and like Giannis, we can like have more conversations like this.
Sounds great.
Yeah. Right.
I hope you guys have a wonderful time hacking away. Enjoy your
Thank you. Thank you.
pleasure.
Definitely. Thank you, guys.
Bye. Thanks.
Thank you. Bye.